Okay, let's start. So let me activate the first command. So here you can see that we're performing image interpolation. I first read the input image from the function. Here I got the input image GPG. I have it in the PubCA folder. Okay, then I create calculate the size of output image. I just multiply dimensions of the input image by scaling factor. Then I create an empty output image by matrix of zeros, and then I create a loop, go through the height and then weight of the image. I find the position of in the input image. So what I mean by that is, so here we have our factor of 2. Input x, input y are coordinates in the input image. I want to find the matching pixel in the input image to that of output image. Yeah, so we have, for example, a pixel in the output image, and I want to find its matching pixel in the input image. So for that, I go through that output image and divide it by our factor, and round it. And then copy the pixel value from the input image to the output image, and then display it. Let's go to the second one. So here we have our function. Yeah, it accepts the input image name, which is secret. Let me find it. Secret PNG. Yeah. So here we have global and local histogram equalization. So first we read the input image and then perform the histogram equalization using histec. Then I display the images using subplot. Then for the next one I specify the block size as per instructions here. And then what did I do here? Okay, I performed the histogram equalization using block proc. So, and then, so here we're doing a local histogram equalization. And as you know, I use this function to apply just a local histogram equalization. I kind of divide the image into 40 by 40 blocks that do not overlap and equalize, histogram equalize each of them, and then we create output image local and also display it like here, and it reveals some interesting figures. You can see kind of silhouettes here, and here the image itself. Now let's see about histogram match. So where's our green forest? Yeah, forest layer. Okay. So what are we doing here? Okay, so those are histograms for each channel of the green forest image, and that's the histogram of the matched image, and that's the output image for matched image. So yeah, first I get the color of each channel of the images for green forest and forest fire. Then I match them using histec function and in hist. Then I combine them using concatenate function. Then I display the original histograms and the final histogram of the matched image, like concatenated image, and then I display the image itself. Alt, yep. So that was it. Now let's try Elena part 0. Okay, so that's our Floyd Steinberg dithering. algorithm. Yeah, so what are we doing here? We first normalize the image by dividing it to 255 here. Well, we first check if we need to convert it to grayscale. If no, then yeah. I also use here if statement to kind of control the function calling. So if the part equals to 0, we're gonna start with Floyd-Steinberg algorithm. So yeah, here we have the levels, variables that determines the level of quantization. I also here turn my image into doubles. Okay, then I have the height of the image and the width of the image. So, and the pixel as the image that I'm gonna be creating now as an output. So I got the pseudocode and turned that into MATLAB friendly code. So I just, yes, we just first, what am I doing? We first put the y coordinates and then x. So our old pixel would be the pixel in the new image, and the new pixel would be a bounded version of the pixel multiplied by level quantization minus 1 and divided by level quantization minus 1, and then I access the dimension of the pixel and assign for that new pixel's value that we just calculated, and for error I just take the difference of the pixels, and here, well, what do we do here is just assign the pixel values to either black or white based on threshold, and here quantization error value is multiplied by these values and kind of assigned to pixels values. And I then also compared how manually implemented Floyd-Steinberg compares to automatically implemented one using the desert function, and we can see that they are pretty much the same. Don't really see the difference, but yeah. Now let's check how our second method fares. So this is cluster dot desert image. I would say it's pretty accurate. Here we see the cluster of dots. Okay, so if part equals to 1, again, implement the same level for quantization, and here we have 2 by 2 cluster dot pattern that I looked up from the internet. And yeah, if it's grayscale, if it's not grayscale, we convert it to grayscale. We create the empty image, and then we just again go through the input image through this loop and pixel by pixel, and then understand whether to place a black or white dot. And here I had the problem where the image was too white, so instead of dividing halftone by levels, I just left a halftone, and so I corresponded the threshold value to halftone rather than dividing by level of quantization. Because if I do it here, let me show you how it's going to turn out. Oh, okay. Yeah, it's too white. So yeah, that was one of the problems. Okay, and here the result is, yeah, just the one that we expected. Okay, let's go through this again. So this is the result. Yeah, so if pixel value is more than threshold, it's white, otherwise it's black. And Okay, yeah, that's it. Thank you for tuning in.